does it mean for two things to be equal? When I write A equals X, what I mean is any equation where you see X, you could swap all the X's with A's and vice versa. So you have this sort of relation. Well, anything you know about A, you know about X, and anything you know about X, you know about A. But what if this relation only went one way? I'm gonna notate this relation with a closed off equal sign. And what this means is that if we have an equation with X, well, we could take that equation and swap all the X's with an A, but not the other way around. We could swap X with A, but not A with X. So suppose we could swap A with X. Well, we could set A equals to 2, because we know 2 satisfies this equation. 2 squared plus 1 equals 5. We also know 1 plus 1 equals 2, so we know 2 things about the number 2. Now look at the right side. If we could replace X with something else, and we could swap 2 with X, and that means that we could swap 2 with X and then with something else. Well, let's choose negative 2 for X. We know we could swap X for negative 2 because negative 2 squared plus 1 equals 5. Using our logic before, we swap 2 with X and then X with negative 2. So we get these two equations. But obviously, we know that 1 plus 1 is not negative 2. So this equality can't go both ways. So we have this one-sided equality with some variable A and some abstract form X, which symbolizes where information could go one way, but not the other way. To help this make sense, let's think of a common word we use in English. Is. You would say a square is a rectangle, but a rectangle is not a square. All dogs are animals, but not all animals are dogs. So when we write A is X, we mean that we could swap an X with an A, but not the other way around. So what we're doing here is we're taking logical operations and we're converting them into algebraic expressions. Think about it. We take the if and only if, and that gets mapped to the equal sign. We get the directional ifs, and that gets mapped to each of the directional equalities, or directional relations. But there are 2 other expressions that are used in logic. And those 2 are the AND operation and the OR operation. So, with these 5 operations, we have what I'm calling a form. Now, you may look at this and say, wait a minute, aren't these the operations for a set? Well, almost, because a set has one operation that's missing here, and that's the includes operation. We don't have an includes operation. And to help that make sense, let's think about the forms of polygons. So there are all these different forms. You could have square, rectangle, it could be a regular polygon, triangle, isosceles, all these different forms of polygons. But take one form of a polygon. What does it mean to have some element X be inside of the polygon? Well, you could look at a graph and say, you know, X represents the vertices. The vertices are elements of the polygon. Or you could look in 2D space. A polygon is something in 2D space. You could look at the set of the outline of the polygon made. So you'd say, oh, the points along the outline are elements of the polygon. Or you could fill in the polygon. All the points inside of the polygon are your elements of the polygon. What I'm saying is that there's not always the well-defined includes operation on the structure you want to work with. So you can think of a form as generalizing the set. So you've seen how we're taking logical operations and converting it into algebraic relations. I think by adding these new directional equalities, we are making the notations of algebra more precise and more expressive in defining the properties of structures. Thanks for watching.